Good day everyone! Welcome to General Chemistry 2. Today, we are going to talk about acids and bases. Centuries ago, substances were first classified as acids and bases by their observable properties. Like the acids in sour candy or lemons, all acids have a sour taste. They are also corrosive to most metals, so people learned a long time ago not to store fruit juices or vinegar in metal containers. In contrast to acids, bases taste bitter and have a slippery feel. Acids and bases change the color of some dyes. For example, bases turn red litmus dye to blue. Acids change it back to red. When acids and bases react in neutralization reactions, their acidic and basic properties disappear. Now, let's define acids and bases based on some scientists. In the late 1800s, a Swedish doctoral student named Svante Arrhenius proposed a definition of acids and bases based on his experiments with electrolytes. Arrhenius proposed that acids and bases produce specific types of ions that other compounds do not. In the Arrhenius model of acids and bases, an acid in aqueous solution produces hydrogen ions represented by H positive, and a base produces hydroxide ions represented by OH negative. So let's have this reaction. Hydrochloric acid combines with H2O to produce hydrogen ion and chlorine ion. So as you can see here, there is the production of hydrogen ion, meaning to say this is an example of an acid. Next, NaOH combines with hydrogen, or NaOH combines with water to produce its ion, which is a sodium ion and a hydroxide ion. So in this reaction, we can consider this as an example of a base because of the production of hydrogen or hydroxide ion. Okay. The Arrhenius model explains how acids and bases neutralize each other. In a neutralization process or reaction of HCl and NaOH, for example, the H from HCl combines with the OH from NaOH to produce water. So, in a reaction, we can have this one. Okay? The hydrogen ion combines with the hydroxide ion to produce water. And this type of reaction is called the neutralization reaction. Okay? So next we have another definition. In 1923, J.N. Bronstead, a Danish chemist, and T.M. Lowry, a British chemist, independently produced or proposed a new theory to deal with the limitations of the Arrhenius model. The Bronstead Lowry theory defines an acid as any substance that can donate, any substance that can donate an H positive ion to another substance. It also defines a base as any substance that can accept hydrogen ion from another substance. Okay, so based on this definition, it covers all the Arrhenius model of acids and bases, and also satisfies the other limitations of the first definition given to us. Okay, so any substance that donates a hydrogen ion is considered as an acid, while any substance that accepts hydrogen ion is considered as base. Next. So in this reaction, as hydrochloric acid combines with water, so the results of this reaction is a hydronium ion and a chlorine ion. Okay? So the H of hydrochloric acid is transferred to H2O to produce a hydronium ion, okay? And then the remaining ion, which is, or the remaining substance, which is HCl, will become independent, and it will be the chlorine ion. So in here, the one that donates, okay, that donates the hydrogen ion is considered an acid. So that is HCl. And the one that accepts the hydrogen ion is considered the base. Okay, so this one is acid. And the one that accepts the hydrogen ion is considered as the base. So this is the base. So this reaction is based on the definition of Bronstead and Lowry. So another reaction, we have ammonia combines with H2O or water. So ammonia combines with H2O, okay, to produce ammonium ion and hydroxide ion. Okay, so the H or the H ion, hydrogen ion in H2O is donated to ammonia, okay, to produce ammonium ion. So in this reaction, the donor is H2O, which is considered to be an acid, while the acceptor is ammonia, which is considered as a base. Okay, so this reaction is still under Bronstead and Lowry theory. Okay, now let's proceed. Bronstead-Lowry bases also include anions such as the carbonate ion CO3 with a charge of -2, which is found in the compound Na2CO3 used to alter the pH of swimming pool water. When added to water, Na2CO3 first dissociates completely into its ion. So in this example, we can have this reaction. Na2CO3 combines with water and it dissociates into its ion, which is Na positive and CO3 with a charge of -2. Now, the CO3 ion acts as a base in water by accepting an H positive from water. So we have here the reaction. So CO3 combines with water to create HCO3 negative and an hydroxide ion. Okay? So the H of H2O is donated to CO3 to create HCO3. So in this reaction, okay, CO3 acts as a base because it accepts the hydrogen ion given by water, which is now considered as an acid. Okay? Next. So we can have another example based on Bronstead-Lowry theory. So let's have letter A. HNO3 combines with water to yield or to create NO3 negative and hydronium ion. Okay? So for letter A, which of what substances is considered to be an acid and what substance is considered to be a base? So for letter A, based on the reaction, okay, HNO3 is considered to be the acid. Why? Because it donates its hydrogen to water. So, from that reaction, it produces or they produce hydronium ion. Now, Since HNO3 is considered the acid because it donates the hydrogen ion, so water now is considered to be the base. Okay? Next, for letter B, SO4 combines with water to produce HSO4 and hydroxide ion. So based on this reaction, what or which of the reactants is considered to be the acid? Okay, so it's water because H2O donates its hydrogen ion to SO4 to produce HSO4. So H2O is considered to be the acid because it donates its hydrogen ion. Now, SO4 now here is the base because it accepts the hydrogen ion donated by H2O. Okay? So letter C, H2CO3 combines with CHNH2 to produce HCO3 and CH3NH3. So now, based on this reaction, which of the following is considered, on the reactant part, which of the following is considered to be an acid? Okay? So the acid here is H2CO3 because it donates one of its hydrogen ion to CH3NH2. Okay? So H2CO3 is now the acid, and the other one, CH3NH2, will now become our base. Okay? So it is easy for us to identify the substances that is considered to be an acid or a base, okay, by just merely looking at the reaction. Okay, we are going to trace where did or which substance donated the hydrogen and which substance accepted the hydrogen. Okay, we can trace it by looking at it at the product side, looking at their products, and by looking at their subscript. Okay, so as you can see here, CH3NH2, okay, it increases into CH3NH3. Okay, so that's the easiest way to identify whether a certain substance is an acid or a base. Okay, next. So we have another example, and you can try this on your own. You can just pause the video and identify which of the substances on the reactant side is considered to be an acid and which of the substances is considered to be a base. Okay, next. Let's proceed with conjugate acids and bases. So what are conjugate acids and bases? When an acid donates a hydrogen ion to a base, the two products differ from the reactants by one hydrogen ion. The product that forms as a result of gaining a hydrogen ion is called a conjugate acid of the base from which it is formed. The product that forms as a result of losing a hydrogen ion is called the conjugate base of the acid from which it forms. Okay? So let's have this example. HCl is an acid and H2O is a base in this reaction. So, as HCl donate its hydrogen ion to H2O, it will create hydronium ion. Okay? And then, it will also create a chlorine ion. Now, the one that accepts the hydrogen ion is considered to be a base, and so the product of that, since it accepted a hydrogen ion, is considered now a conjugate acid or conjugate acid of the base. Okay? Next, when the acid donates the ion to the base, it releases its ion, and so the resulting product, okay, for the acid will only be an independent ion for this example, and that is Cl, or chlorine ion. And so the chlorine ion here is considered to be the conjugate base of the acid. Okay? So that's how we identify conjugate acids and bases. Okay, so let's proceed. Conjugate acid-base pairs always differ by one hydrogen ion. The conjugate acid of a substance has one more hydrogen than the conjugate base of a substance. The conjugate base of an acid is what is left after the acid donates a hydrogen ion to another substance. The conjugate base then has one less hydrogen atom in its formula and a decrease in charge of 1. Okay? So, in this reaction, we can see here the difference in one hydrogen ion. Because as the acid donates its hydrogen ion to the base, okay, the resultant or the resulting products, okay, the conjugate acid has a one hydrogen ion more, okay, compared to the conjugate base. Okay? And so, because of the donation of hydrogen ion, the conjugate base has a decrease, or there is a decrease on its charge by 1. So, it will become negative. Okay? And in here, there is an increase. Okay? That's why it's positive. Next. So, let us identify the conjugate base for each acid. So, all of these examples, or all of these given substances are acid. Now, let's identify its conjugate base. So, for letter A, as HOCl releases or donates its hydrogen, the resulting conjugate base will become OCl, and the charge of this will be negative because of the reduction of hydrogen ion and the decrease on its charge. Okay? Next, for letter B, as H2PO4 releases one of its hydrogen ion, the resulting conjugate base will become HPO4 with a charge of -2. Okay? So, that will be its conjugate base. Okay? Next, for letter C, we have H2O, and so the release of its hydrogen ion, it will have its conjugate base as OH negative. Okay, so these are the conjugate base for each acid. Okay, next. Identify the conjugate acid for each base. So all of these examples, or all of these given, are bases. Now, they are the ones who's going to accept the hydrogen ion given off by an acid. So for number 1, what will be its conjugate acid? If F negative will accept a hydrogen ion, so it will become HF. Okay? Next, for number 2, as HCO3 accepts a hydrogen ion, the resulting conjugate acid will be H2CO3. This is number 3. Okay? Next, for H2O, okay, what will be its conjugate acid? As it accepts a hydrogen ion, it will become H3O, or hydronium ion. Okay? So all of them will have, okay, the hydrogen ion. Okay? So there is an increase in hydrogen ion, And so their charges will have also an increase. Okay? So all of these conjugate acid will have an increase in charge, and so they will become positive. Okay? So let's proceed. Now let's proceed with strong and weak acids and bases. So let's have the definition first of strong acids. Strong acids ionize completely when dissolved in water. When the strong acid HCl ionizes in water, the resulting solution consists of only H, O, a chlorine ion, and H2O. It contains essentially no unionized HCl or hydrochloric acid. Okay? So strong acids, they are completely dissolved in water. Next. For strong bases dissociates completely when dissolved in water. The strong base sodium hydroxide or NaOH dissociates completely in water to form Na and OH. So these are the ions, okay? Essentially no undissociated NaOH remains. So they are completely dissolved in water. So we have here common strong bases. Okay? So as you can observe, strong acids and strong bases, they are completely dissolved in water. Okay? Next. Now, any acid that is not a strong acid is a weak acid, obviously. So a weak acid does not ionize completely when dissolved in water. An equilibrium forms between a weak acid and its conjugate base. So both the reactants and the products are present in the solution. So in here, we have here the common weak acids, and as they are combined to water, they do not dissolve completely. Okay? Instead, they form an equilibrium. So the weak acid forms an equilibrium with its conjugate base. Okay? So that is for weak acid. Next, a weak base does not completely ionize when dissolved in water. An equilibrium again forms between a weak base and its conjugate acid. Now, we have here the table which consists of common weak bases. So as you can see, or as you can observe, for weak bases and acids, they do not completely ionize when dissolved in water, but instead they form an equilibrium between their conjugate base, acid or base pairs. Okay, so now we are going to learn how water acts as an acid and a base. Water can act as both a Bronstead acid and a base. Between two water molecules, one can give off a proton, leaving the hydroxide ion, and the other can accept this proton to become a hydronium ion. This reaction is referred to as the self-ionization or auto-ionization of water. It occurs because of the amphiprotic nature of water. That is, it can act as both a proton donor and an acceptor. The ions exist in equilibrium with the water molecules. So we have this diagram, or we have this reaction. A water molecule here and another water molecule here combines with one another to form, okay, a hydronium ion and a hydroxide ion. Okay? So we can simplify this one with this chemical reaction or chemical equation. So there is an equilibrium. Okay? So the equilibrium expression for the ionization or auto-ionization of water is written as Kw is equal to the quantity of H3O positive and OH negative, or hydronium multiplied by the value of hydroxide ion. Now, the equilibrium constant of the reaction is called the ionization constant of water, represented by Kw, which has a constant value of 1 times 10 raised to negative 14 molarity. Okay? At 25 degrees Celsius. The kW allows for the calculation of either the hydronium or hydroxide ion concentration when the other value is given. Okay? So let's have this example. So for example, if the hydronium ion is 6.2 times 10 raised to negative 5 molarity, then the hydroxide ion is calculated simply as this one. So we have Kw is equal to hydronium ion times hydroxide ion. Now, as said earlier, the constant value of Kw is 1 times 10 raised to negative 14 molarity is equal to, what is the value of the hydronium ion? We have 6.2 times 10 raised to negative 5 molarity. And we have here the hydroxide ion. Now, so that on one side of the equation, it will only be the hydroxide ion. Divide both sides by 6.2 times 10 raised to negative 5 okay, so it will give us an answer of 1.6 times 10 raised to negative 10, and the unit will be molarity because we are talking about its concentration. So this will be the value of, okay, OH, or the hydroxide ion. Okay, so in a neutral solution, the hydronium and hydroxide ion concentrations are equal and can therefore be calculated by taking the square root of the constant. So we have here Kw is equal to the hydronium ion and the hydroxide ion. Okay, so since they are equal to 1.0 times 10 raised to negative 14 molarity, we are going to get the square root of the constant. Okay, square root of the constant. So we can have here in the equation 1.0 times 10 raised to negative 14 is equal to, now we can manipulate here since the hydronium and the hydroxide ion is equal or are equal. Okay, we can have here, we can represent the hydroxide ion with the hydronium ion. So we can have here H3O positive squared. Okay, so because they have equal concentration, so we can manipulate the formula. Now let us get the square root. Okay, so the value of the hydronium ion, okay, it will now become 1.0 times 10 raised to negative 7 molarity. Now, since the hydronium ion is equal to the hydroxide ion, so the hydroxide ion is also equal to 1.0 times 10 raised to negative 7 molarity. So that is the solution in order for us to get, okay, the values of the hydroxide and hydronium ion when the solution is neutral. Okay, when the solution is neutral. Next. Okay, so when the solution is neutral, okay, so H or the hydronium ion is equal to the hydroxide ion. When the solution is acidic, the hydronium ion is greater than the hydroxide ion. And when the solution is basic, the hydronium ion is less than the hydroxide ion. So just remember this diagram, okay, in identifying whether a certain solution is neutral, acidic, or basic. Okay, next. So, let's compute. So, compute the corresponding hydronium or hydroxide or hydronium ions in each of the following conditions. Okay? Describe the condition as acidic or basic. So, let's have number 1. We have the value of the hydronium ion, which is equal to 8.6 times 10 raised to negative 4. So, using the formula, Kw is equal to the hydronium ion, okay, and times the hydroxide ion. Okay, we are going to look for the hydroxide ion. And if you're going to remember, the constant value of the the constant is 1.0 times 10 raised to negative 14. Okay, substituting now the value, we have 8.6 times 10 raised to negative 4. We have here the hydroxide ion. So, in order for us to get the value of the hydroxide ion, we are going to divide both sides by 8.6 times 10 raised to negative 4. 8.6 times 10 raised to negative 4. So, we have the value of the hydroxide ion, which is equal to 11.62, or let's have the two decimal places, 11.63. Okay, 63 times 10 raised to negative 12 molarity. So that will be the concentration of the hydronium or hydroxide ion. We have 11.63 times 10 raised to negative 12. Okay, now let's try another one. Let's have number 2. So since we have the given hydronium ion concentration of 1.4 times 10 raised to negative 11, following again the solution, we have Kw is equal to the hydronium times the hydroxide ion. Okay, so we have here 1.0 times 10 raised to negative 14 is equal to, substitute the values, we have 1.4 times 10 raised to negative 11. We have here the OH. Okay, so since we are looking for the value of OH, we divide both sides by 1.4. 1.4 times 10 raised to negative 11. 1.4 times 10 raised to negative 11. Okay, so the value now of OH is 0.000714, or in scientific notation we can have 7.14 times 10 raised to negative 4. Okay, that will be in molarity. Okay, so the value of OH now is 7.14 times 10 raised to negative 4. Okay, I hope you followed the procedure of the solution. Okay, let's have number 3 with the value of the concentration of hydroxide ion. Okay, the value is 2.7 times 10 raised to negative 5. Okay, so for number 3, following again the solution, so Kw is equal to a hydronium ion times the hydroxide ion. Okay, so Kw is equal to 1.0 times 10 raised to negative 14 is equal to hydronium ion, and then the value of the hydroxide ion, which is 2. Okay, what is the value again? 2.7. 2.7 times 10 raised to negative 5. Okay, so that H3O will be on one side of the equation. We divide both sides by 2.7 times 10 raised to negative 5 times 10 raised to negative 5. So our value for H3 or the hydronium ion will be 370.37, okay, times 10 raised to negative 12. Okay, so this will be the value of the hydronium ion for number 3. Okay, now let's proceed with measuring acidity with pH. In 1909, Danish chemist Søren Peter Lauritz Sørensen introduced the pH scale as a way of expressing the concentration of the hydrogen ion in dilute solutions. pH, an abbreviation for power of hydrogen, indicates the acidity or basicity of a solution. The P refers to the power or exponent of the hydrogen concentration. The pH of a solution is mathematically defined as the logarithm of the reciprocal of the hydrogen ion molar concentration. So we have here, okay, we have here the formula. Okay, so pH is equal to the logarithm, okay, the logarithm of the reciprocal, okay, of the reciprocal of the hydrogen molar concentration. Okay, so if we are going to simplify this one, we can have this formula, logarithm times the hydrogen molar concentration raised to negative 1, or we can have this negative logarithm times the molar concentration of the hydrogen ion. Okay, next. So acidic solution have pH level greater than, pH level less than 7 because the hydrogen ion is always greater than as implied by the negative logarithm. Alkaline solutions have, okay, greater than 7 because the hydrogen ion is less than 1 times 10 raised to negative 7. So for alkaline solutions, it is more convenient to use the term POH or power of hydroxide, which is based on the hydroxide. So we can have the formula here. POH is equal to the negative logarithm of the hydroxide concentration. Okay, so general steps in solving for the pH and POH level of substances. So first one, we need to identify the given and then write the formula for pH or POH, and then number 3, substitute the values in the formula, and then number 4, solve properly with complete solutions. Okay, so first we have this example. So let us write the given. We have here the molar concentration of the hydrogen ion, which is equal to 0.01 or 0.010 molarity. Okay, so using the solution, pH is equal to the negative log of the hydrogen ion. Okay, so we can now, for letter A, this is for letter A, this is for letter B. Now we can now substitute the values. So pH is equal to negative log times, substituting now, we have 0.010 molarity. Okay, so our pH value will now become 2. Okay, so this will be the pH value, and since it is less than 7, so this pH value, this is considered acidic. Okay, So that is the solution for number 1. Okay, now let's proceed with number 2. What is the concentration of the hydrogen ion in a solution with a pH of 4.73? So let's write the given. We have pH is equal to 4.73, and we are looking for the concentration of the hydrogen ion. Now, letter B, we have the formula pH is equal to negative log times the concentration of the hydrogen ion. Now, substituting now the values, okay, we have 4.73 is equal to negative log times the hydrogen ion. Now, in order for us to get the value of the hydrogen ion, okay, we divide both sides by negative log. Okay, so the hydrogen ion, okay, will now be equal to 4.73 divided by negative log. Now, we cannot input, okay, this formula in our calculator. So, simplifying this formula, we can have, okay, hydrogen ion is equal to the anti-log of negative 4.73. Okay, now, how are you going to input that in our calculator? So, first, we need to press, okay, in our calculator, we have shift. Okay, and then, after pressing shift, press log. Now, the screen on your calculator will show this value, 10, and then there's a box here. Okay, in the box on the upper right, okay, in this box, you're going to input negative 4.73. So, if you're going to input that, okay, in your calculator, we have 10, okay, raised to negative 4.73. Okay, then, you now press equal or equals. Okay, so the value that will show will now be equal to, okay, 1.86 times 10 raised to negative 5. So that will be the value of the hydrogen ion. Okay, so when you encounter similar types of problem, okay, that requires you to divide the value of pH by the negative log, it will give us this formula, okay, the antilog of the pH. Okay, so if you're going to input that in your calculator, press shift and then log. Okay, it will give you what it will present on your screen 10, then a box. Then on the box, you're going to write the value, okay, like here, the value of the pH, okay, negative value, okay, negative value of the pH, and then press equals, and it will give you, okay, the answer for the concentration of hydrogen. Okay, I hope you followed the steps. Shift, log, then input the negative value of the pH, and then press equals, and then that will be your answer. Okay, so next, okay, number 3, calculate the pH of a 0.00015 molarity of NaOH solution, wherein NaOH is a strong base and completely dissociates in water. Now, for this problem, we need to remember one formula. Okay, so we have here the formula pKW is equal to the sum of the pH and pOH. Now, the value of pKW is always equal to 14. So, pH plus POH. This is always equal to 14. Okay, now, let's write the given. We have letter A, the value of okay, the value of NaOH. Okay, so NaOH, since it is a strong base, so we have here the OH. Okay, this will be the OH value, which is equal to 0.00015 molarity. Next, we are going to solve for the pH. Now, for letter B, we are going to use the formula or place the formula. Now, since it is we are looking for, or we have the given OH, okay, not H, and if you can remember, we have the formula POH, okay, for bases. We can use that, okay, which is equal to negative log times OH. Okay, so remember, if the given is an OH, you can use this formula. POH is equal to negative log times OH. Okay, now for letter C, we need to substitute the values. Okay, so POH is equal to negative log times 0.00015 molarity. Okay, so the value for the POH will be 3.82. Now, this is the value for the POH only. Now, we now proceed here. Okay, so we can see in this formula, okay, that POH plus pH is equal to 14. And we are looking for the pH, not the POH. So, substituting now the values, we have 14 is equal to pH plus 3.82. Now, in order for us to get or to have the pH on one side of the equation, we need to transpose 3.82 to the other side of the equation. So, we have here pH is equal to 14 minus 3.82. And so, the value of the pH, okay, the value of the pH will be pH is equal to 10.18. Okay, so this is the pH value. So, that's how you calculate for the pH when the given is an OH. Okay, so 10.18. And so, since it is greater than 7, this is a basic solution. Okay, so always remember this formula, okay, where pKW is equal to the sum of pH plus POH. Okay, next. Okay, now let's complete the table. Okay, so first we are looking for the value of the pH. So for letter A, we are looking for the value of the pH. And we have here the value of the H. Okay, so using the formula, we have pH is equal to negative log times H. Substituting the values, we have negative log times 3.6 times 10 raised to negative 5. Okay, so we are going to have the value 4.44. So that will be the pH value. So we have here, we can write here the value 4.44. Okay, next, we are going to get the POH value. And if you can remember the formula again, pKW is equal to pH plus POH. So for letter B, we can have Okay, pKw is equal to pH plus pOH. Okay, so we have here 14 is equal to the value of the pH, which is 4.4 plus pOH. So we have pOH is equal to 9.56. So that is the value of pOH. Okay, so we can input here 9.56. Okay, now we are going to solve for the OH. Okay, using the formula of the POH, POH is equal to negative log times OH. Okay, so the value of POH is 9.56 is equal to negative log OH. Now, if you can remember the shift, okay, shift log, okay, so the OH value using the anti-log, okay, so that will be the anti-log of negative 9.56. Okay, so OH now, okay, our value for OH will be 2.75 times 10 raised to negative 10 molarity. Okay, so in this part of the equation, you're going to use the shift log. Okay, in your calculator, shift log, and then input the value, and then it will give you the answer 2.75 times 10 raised to negative 10. So we have here 2.75 times 10 raised to negative 10. Okay? Okay, for the next item, the only value we have is for the POH. So, we have the value 4.48. Now, we have here 4.48 for the POH. Now, we are looking for the hydrogen ion, the pH, and the hydroxide ion. Okay. So, first, it will be easier for us to do the hydroxide. So, we have here letter A. We have POH is equal to log times the hydroxide. Okay. So, substituting the values, 4.48 is equal to negative log times OH. And so, you do the shift log. Okay. So, OH will now be equal to, okay, shift log or the anti-log of negative 4.48. Okay, so OH will now be shift log and then input the value negative 4.48. So the answer will be 3.31 times 10 raised to negative 5 m. Okay, next. So we have here the OH. Okay, 3.31 times 10 raised to negative 5. Let's input that. 3.31 times 10 raised to negative 5. So we have here m. Okay, next. We're going to look for the pH. So for the pH, we have letter B. pKw is equal to pH plus pOH. Okay, so we have here 14 is equal to pH plus 4.48. Now, we have here pH is equal to 14 minus 4.48. 14 minus 4.48 is equal to, pH is now equal to 9.52. Okay, so that will be the value for the pH, 9.52. Okay, so let's input it here, 9.52. Okay, next. So for letter C, we are looking for the hydrogen ion. So since we already have the pH, we have pH is equal to negative log, okay, times the hydrogen ion. Substituting the values, we have 9.52 is equal to negative log times the hydrogen ion. Now, for the value of hydrogen ion is equal to the anti-log, okay, of the negative 9.52. Okay, so if we are going to get that, input that in our calculator, we have shift log, okay, then input the value negative 9.52. It will give us the answer of 3.02 times 10 raised to negative 10. Okay, so this is the value of our hydrogen ion. 3.02 times 10 raised to negative 10. So we can input it here. 3.02 times 10 raised to negative 10. Okay? Ayan. So that will be our values now. We were able to complete the table. Okay? So that's the process on how you're going to compute for the pH, the pOH, and the ions for hydrogen and the hydroxide. Okay? The values. Okay? That will be all. Thank you for listening. Thank you for participating in our session, in our video lecture session in chemistry. I hope you learned something today. And if you have questions, you can just ask your subject teacher about it. Okay? Thank you very much for listening and see you next time in the next video lecture for Chemistry 2. Thank you very much and God bless.